Regression is a powerful tool for creating ceteris paribus comparisons and identifying the independent effect of one variable on another. But omitted variable bias makes it difficult to know for sure if we have accounted for all we need to. This problem is solved by randomized controlled trials because people are randomly selected and assigned to a treatment or control group. But when an RCT isn't feasible, we need to make do with what we have. One thing we can do is search for natural events which act like randomized controlled trials, events which arbitrarily assign some people to a treatment. Economists exploit these natural experiments for causal identification. We have good estimates of the effect of money on happiness because we can compare lottery losers to lottery winners. The lottery effectively randomly assigns people to the treatment group of being a millionaire. If we compare them to the people who played the lottery but did not win, we have a quasi-experiment where we know how money impacts lottery players. We can also exploit differences in the law as a natural experiment. Does banning smoking in restaurants improve people's health? We can compare people who live very close to a border, where on one side of the border smoking is banned and on the other it isn't. Do people living on the banned side see an improvement in health outcomes? Do those restaurants suffer from lost business or maybe better business? By comparing them to a group of people who are pretty much the same on either side of the border, we can get the counterfactual and estimate the causal impact. Natural experiments have a long history of shedding light on important questions. Back in 1854, doctors thought cholera, a deadly disease which causes dehydration, spread through the air. John Snow, no, not that John Snow, but this John Snow, exploited a natural experiment to prove everyone wrong. He mapped out where people in London were being diagnosed with cholera and showed that it corresponded directly to the use of a particular water well. He concluded that cholera must spread through the water supply. Soon, people started boiling their water, which prevented the spread of cholera. That was itself a major discovery, but it advanced the germ theory of disease, which correctly identified how people contract many diseases. Economists have many methods of constructing the counterfactual for a treatment group for one of these natural experiments. One is called differences in differences. Economists believe that the major cause of the Great Depression was a crisis of bank failures. Back in the 1920s and 30s, there wasn't any deposit insurance, which meant that if your bank went under, you lost all of your money. When confidence was lost, bank customers rushed to withdraw their money before the bank failed, and these bank runs ended up causing the failures. In 1913, the U.S. had set up a central banking system designed to stop bank runs and prevent financial panics. When banks are in trouble, the central bank embarks on a policy of easy money to keep them afloat. But many economists worry that these policies might backfire, and bank bailouts just lead to banks taking on more risk and failing more often. These days, central bank policy is decided nationwide, but back in 1930, each of the district banks could do pretty much whatever they wanted. This creates an opportunity for a natural experiment. We need to find a region where we would expect all other policy responses to the Great Depression to be the same, and the only difference would be whether or not their Federal Reserve District embarked on a policy of easy money. The problem is that won't work across state lines, because different states had different programs in response to the Depression. But here, in Mississippi, you have one state split into two different Federal Reserve districts. And as it turns out, District 6, covering southern Mississippi, embarked on a policy of easy money many months before District 8 did in northern Mississippi. That is what motivates a difference in difference analysis. The key assumption for differences in differences is parallel trends. We want to compare banks near the Federal Reserve border to one another and see that prior to the banking crisis, they followed a similar trend. These two lines are different, but parallel, suggesting that if one goes up, so will the other, and if one goes down, so will the other. Then we look at what happens when the banking crisis hits. District 6 applied the treatment of easy money, and we see that they lost fewer banks than District 8. Then, after the crisis, the trends returned to their parallel form. We can visually confirm the ceteris paribus comparison. The only difference between these groups is which Fed policy they were under. From this data, we're essentially constructing a counterfactual, assuming that the trends would have remained parallel the entire time, if not for the treatment. If we first take the difference within each group, comparing the before and after, we can then take the difference in differences. Here, we find that District 6 probably had about 19 more banks than it would have had if they did not implement the easy money policies. Instead of losing 14 banks, they would have lost 33, just like District 8. Differences in differences is a very simple and intuitive approach to natural experiments. And when the underlying assumptions, like parallel trends, are robustly checked, it serves as a quasi-experiment that allows for causal identification. Regression discontinuity is another important tool in the econometrician's toolkit. An example comes from a paper by Angrist and Levy, which sought to identify the impact of class size on test scores. It would be nice to conduct a randomized controlled trial, where some students are randomly assigned to a big class and others to a small class. But that would be pretty expensive and hard to convince people to try. But Angrist and Levy found a natural experiment in an unofficial policy implemented by schools in Israel. The 12th century rabbinic scholar Maimonides wrote down a rule for schools to follow. When a class reaches 40 students, split the class into two. This rule was by no means the law, but Angrist and Levy showed that this rule was being followed by some extent by schools in Israel. The key assumption for regression discontinuity is that the cutoff is binding. As long as a significant proportion of classes with 39 students remained 1, but once enrollment reached 40, it was split into two classes of 20, then we have a convincing counterfactual. We can compare the test scores of students in schools with 39 pupils to those with 40 pupils. There aren't likely to be any other differences between those groups other than the application of Maimonides' rule, which reduced one group's class size. The way we estimate the treatment effect for regression discontinuity is to estimate two regressions, one for people below the cutoff and one for people above it. Using the regression equation, we can predict the test scores of students who would fall exactly at the cutoff and compare. The difference in the predicted test scores could only be due to the treatment applied at the cutoff, and so that represents the treatment effect. In their latest analysis, Angrist and Levy show no effect of class size on achievement, which they replicated in another paper which used data gathered since their first publication. Regression discontinuity offers another intuitive approach to causal identification. When we spot this discontinuity in a trend, this jump in where the data falls, and that discontinuity corresponds to some policy, then the difference in outcomes must be due to the policy. Both difference in differences and regression discontinuity are applications of a broader research design called instrumental variables. Instruments are events which influence the likelihood that a person will receive a treatment. When there isn't a clear before and after, or a discontinuity in policy, we can use regression to take advantage of the natural experiment. Here is an example. A person's day and month of birth significantly impacted the likelihood they would be drafted into the Vietnam War. We can use regression to predict service in the Vietnam War using date of birth, and then use those predictions to predict their wages later in life. The key assumption for instrumental variables is that there's no other way for the instrument to affect the outcome except through the treatment, which we call the exclusion restriction. For the impact of service in Vietnam, we are assuming that if your date of birth can predict your wages later in life, there's no possible explanation for that other than the fact that your date of birth impacted the likelihood of serving in Vietnam. During the draft, the government would randomly draw dates of birth out of a big container. In 1970, the first date they drew was September 14th. Anyone of draft age who was born on September the 14th was likely to be drafted that year. And they kept drawing until every date had been drawn, putting the dates in a random order. The military then went in order of the dates drawn, calling everyone with a certain date to service until they had enough men for the war. In 1970, a person born on July 13th was likely to be drafted, since their date was 42nd in line. Of course, it wasn't a sure thing. Some people received deferments for school or other reasons, but they probably weren't any more likely to get a deferment than someone born on July 14th. Those born on July 14th were numbered 331 in the draft, which meant they were unlikely to get drafted even without a deferment. Let's take a step back and think about this. Most people felt that service in Vietnam had negative effects on your career and income, but it's hard to really know that. As made famous by CCR in their song Fortunate Son, if you were born to a rich family, you were a lot more likely to get yourself a deferment from the draft than somebody born to a poor family. But you're also probably more likely to make a lot of money later in life if you were born to a rich family. Perhaps it's just unfairness causing both service in the Vietnam War and lower wages later in life. Certainly, unfairness is an omitted variable, biasing the comparison between those who served and those who didn't. But unfairness is pretty hard to measure. Josh Angrist, who wrote this paper on the effects of the draft, found a way to cut through the mess. There's just no other reason to believe that the average person born on July 14th would make more money than the average person born on July 13th, except by way of service in the Vietnam War. But the group of July 13th and 14thers is too small. To get a big sample, he needed to use everyone. So he used the date of someone's birth to predict whether they served in Vietnam. Then he used those predictions to predict their wages later in life. Econometrics shows us that if the assumption is right, if there really is no other way date of birth impacts wages, then the coefficient found in the second stage is the causal impact of service in Vietnam on income. Angrist found that these veterans earned 15% less than comparable non-veterans, identifying a large and important additional cost of that war on American citizens. One of my untested hypotheses is that this brief survey of economic methods is comprehensible. We've gone through it pretty fast and without too much technical detail. I hope it still made sense. Here are some quick conclusions I hope we shed some light on. Like any science, economics starts with some theories. Economists communicate their theories through mathematical models, which logically walk us from assumptions to a prediction. Economists check their predictions empirically. If we predict a higher price causes people to buy less of something, we should be able to observe that correlation in the real world. However, correlation is not causation. We may have a theory to explain it, but that doesn't make it true. Causal identification needs good research design. The gold standard is the randomized controlled trial, which produces a clear and correct counterfactual in the control group. When an RCT is not feasible, though, natural experiments are a good second choice. Natural experiments have added assumptions, like parallel trends, a binding cutoff, or the exclusion restriction. Good economic research does the due diligence of checking the validity of these assumptions with the data they have. Anyway, I guess my point is, it is hard work, and I think is useful to know a little bit about it. Nevertheless, I feel a lot like Alan Grant in Jurassic Park, teaching that kid about raptors. I guess what I'm trying to say is...
So, try to show a little respect.
Okay.